We're living in this incredible age of medicine, and one of the biggest frontiers right now is immunotherapy. So today, we're going to zoom in on its special forces, these powerful, super precise drugs called monoclonal antibodies. Okay, so think about it like this. For years, a lot of medicines have kind of been like hammers, right? They're powerful for sure, but they can cause a lot of collateral damage, what we call side effects. Monoclonal antibodies, they are totally different. They're like a key, one that's designed to fit one single specific lock in the body. That precision is exactly what we're going to unpack. So, to really get what makes these keys so special, we got to look at how they're built. They are just fundamentally different from a common drug you might think of, like aspirin. And that difference, well, it changes everything. On one side, you've got your small molecule drugs. These are simple chemicals, the kind you can often just swallow in a pill. But on the other side, you have monoclonal antibodies, or MABs. These things are massive proteins. And because they're so big, they can only target things on the outside of our cells. It's also why you can't take them as a pill. Your stomach would just digest them like food. That's why they always have to be given through an IV or an injection. Okay, so what does this all mean for a patient? Well, there are some huge advantages. These big proteins stick around in your body for days, even weeks, which means you don't need to take them all the time. Plus, since they aren't processed by the liver like so many other drugs, you get way fewer drug interactions. But, and this is a big but, because they're so large and complex, your body can sometimes see them as a foreign invader and actually create antibodies to fight the medicine itself. And that whole idea leads us to one of the coolest parts of this story. You've probably heard those super complicated drug names that end in MAB, right? Well, they're not random at all. There's a secret code hidden right there in the name that tells you exactly where the antibody came from and even gives you a hint about how likely your body is to attack it. You can actually see the evolution right here. The very first MABs ended in OMAB because they were made from 100% mouse protein. And while our immune system is pretty good at spotting something that isn't human, so scientists got clever and created ZimMab drugs. These are part mouse, part human. They're called chimeric. It was better, but they could do more. Next up were the Zumab drugs, which are humanized, so mostly human. And finally, we get to UMAB drugs, which are 100% human. The takeaway is simple. The more human the drug is, the less likely your body is to see it as an enemy. So we know what they are, and we know how to decode their names. But how do they actually work? To see them in action, let's look at one of the most common and important examples out there, anti-TNF therapies. The whole strategy here is called cytokine neutralization. Just think of cytokines as these tiny little messenger molecules that are running around your body shouting inflammation, inflammation. This therapy works by basically intercepting those messengers and taking them out of the picture before the message gets delivered. It's not about shutting down your whole immune system. It's about removing one very specific, very loud inflammatory signal. And in a whole bunch of autoimmune diseases, that main messenger, the cytokine causing all the trouble, is called tumor necrosis factor, or TNF. It's a major driver of inflammation. So scientists brilliantly designed a monoclonal antibody, key, specifically for the TNF lock. The antibody just grabs onto TNF and neutralizes it, stopping it from ever triggering that inflammation cascade. And this is where it all connects. Look at these common anti-TNF drugs. See that first one, infliximab? That iximab tells us it's chimeric, part mouse. Then you've got adalimumab. That UMAB ending means it's fully human, and that means a lower risk for an immune reaction. You can also see the IV and injection routes we just talked about. That last one, certolizumab, it's a little different. It's what's called a pegylated Fab, which is just another clever way to help the drug work better and last longer in the body. The impact of this is just massive. These drugs are used to treat a whole range of really tough diseases, from rheumatoid arthritis to Crohn's disease and psoriasis. For literally millions of people, just neutralizing that one little TNF signal has been absolutely life-changing. So what's the big takeaway from all this? What does this amazing technology really mean for the future of how we treat disease? It really all comes down to this. We are moving away from that chemical hammer and towards the biological key. It's a huge shift from treatments that just carpet bomb the body to therapies that can target a single problem-causing molecule. This right here is the heart of precision medicine. What these drugs really show us is that the blueprint for the next wave of powerful medicines might not be found in a test tube, but might already exist inside our own bodies. Which leaves us with a pretty fascinating thought. What other biological locks are out there, just waiting for us to design the perfect key?